Welcome to today's webinar. We're excited that you're joining us today. We'll get started in just a few seconds. All right, let's go ahead and get started. Again, welcome to the webinar today. My name is Matt Cederberg, and Greg Vernon will be presenting the webinar along with me today from Coreform. Today's topic is Coreform Cubit and how to handle dirty CAD and build a mesh from dirty CAD. With the webinar, as you have questions, feel free to ask us in the Q&A throughout the webinar, and this will be recorded. And with that, let me turn the time over to Greg.
Okay, thanks, Matt. Yeah, so as Matt said, the topic of today's webinar is to investigate what dirty CAD is and how we can handle dirty CAD in Cubit, and specifically how we kind of need to treat or maybe kind of dance around dirty CAD to make the mesh. So a few things that hopefully you'll come away with is like top level things is hopefully you'll understand why CAD can be broken or dirty, and then how it might be recoverable or unrecoverable, and how you can avoid accidentally creating dirty CAD in your workflow. We're going to talk a little bit about absolute tolerance and why that's critical to understand in the Cubit workflow, as well as a few kind of key operations that you may find are helpful for dealing with absolute tolerance. And then we're also going to talk a little bit about some direct editing capabilities of the CAD BREP geometry that you can do in Cubit, that are kind of tools of the trade to get around or to handle this dirty CAD. So yeah, just as a quick reminder, I'm sure that everyone on is familiar with Cubit, but with Coreform Cubit, if you're not, Coreform Cubit is an advanced meshing platform for challenging simulations. It has everything from triangle and quad meshing to tetrahedral and hex meshing, with pyramids to handle interfaces between those meshes, applying sets for boundary conditions and materials, as well as an integrated Python API for ease of scripting. And we're going to actually explore that a little bit today as well. So with that, we'll just jump right in. Kind of really three main causes of dirty CAD. And what I mean by dirty CAD is I want to kind of differentiate it between just like broken CAD. Broken CAD is essentially where the geometry is maybe so bad that there's just no way that the model can be recovered without just losing a lot of information or making some decisions. And we tend to only see that when you are dealing with really, really old legacy parts. But dirty CAD is just kind of where there's maybe some imprecisions or some slight differences between representation. They can cause issues when you're trying to build a mesh on it. They maybe don't necessarily come up in other applications of CAD. Whereas again, broken CAD, you really can't even build parts with a broken CAD model. So again, just to talk about these reasons, we have to remember that CAD is primarily used today to create drawings, and part defining drawings, where it's more about the features that matter. It matters that there's a fillet here with a certain radius. It doesn't really matter what the specific BREP topology is or how that specific BREP topology might be then encoded in the CAD format. It doesn't matter if it's a spline versus being an analytic circular arc. It just matters that there's a feature there that someone could put a measurement to in a drawing. There's also then these translations between CAD formats, especially if a neutral format like STEP or IGES has been used as an in-between format, that all these different CAD platforms, whether you're SolidWorks or Creo or CATIA, they might have different kind of features or functionalities that maybe the other softwares don't have. And so if they want to translate to another format, they have to do a lossy translation. And oftentimes these neutral formats also kind of have like a standard that maybe everyone kind of agrees upon, but that maybe there are some, again, special functionality in those CAD applications that can't be directly translated to those. And so because of that, we just get some errors that show up. And then lastly, there's this inherent limitation in the mathematics of the CAD geometry, which we're going to spend a little bit of time talking about. And this is really where and why there's kind of this need for tolerance in CAD, in the actual CAD BREP geometries, that you may not be as familiar with. So just to kind of, again, recap, just these drawings versus FBA. In the drawing, I just care about the fact that I have a feature and I can say that this feature has a certain radius. Our FBA tools or our meshing tool need to be able to take the CAD BREP topology here highlighted in orange and subdivide into elements to be able to evaluate those curves to determine where to place nodes of elements. And so there's just a higher level of correctness that's required by meshing applications. For this lost in translation idea, here's an example where there's a native Asis geometry that you might have, say, constructed in like a CATIA or a SolidWorks, CATIA or Abacus or something. So if you export this to IGES, there's a surface here that couldn't be represented in this IGES file. And so that surface has just disappeared and gone. And so whether you're in a different downstream application or Cubit, in this case, we just can't even work with this geometry. And we'd have to, say, try to reconstruct this geometry in Cubit, or maybe try to hopefully export to a different format that can support that. Now, this inherent limitation in CAD is that we tend to see on our screens a nice, pretty looking CAD picture, but actually behind the scenes, all of these surfaces are actually a bunch of trimmed surfaces. And then here you have like this exploded view of these trims. What CAD BREP is then trying to do is describe how these different trimmed surfaces are then connected to each other. But if during this trimming process, you can imagine if you're using scissors to cut these out, if you don't have great precision in how you've trimmed or cut these surfaces, that can then lead to gaps in the model that then cause issues again when we're trying to build an FBA mesh. And so a big limitation of this really comes from the use of splines in CAD. Again, most of these surfaces that we see here are actually what are, I'm going to call them analytic surfaces. They're literally encoded as a plane or as a conical surface, like a cylinder or a torus. And so they're precise. But sometimes there are like these gaps in geometries, or there's a complex fillet that can't be represented by one of those sorts of almost kind of like platonic solids, if you will. And so we use splines. And a common spline to use are cubic splines. So if you have these two surfaces, the intersection, again, of those trims is an impractically high degree for us to represent exactly in the computer. So instead, all the different CAD applications approximate those trims with a lower order approximation. And then that has lost information. We've introduced gaps into our model. And what we'll see that spline surfaces are oftentimes the cause of a lot of the dirtiness in CAD. We'll actually even see that. So if we have these CAD models that then have these inherent gaps, our tool needs to then understand, hey, if there is a small gap that's below some value, treat this as if it is watertight. And so just as an example here, I've exacerbated this issue where maybe I got two surfaces that are supposed to intersect kind of along the middle of these two surfaces. And I've just drawn on here like this absolute tolerance kind of tubes. So I think it's helpful to think of, or to try to imagine that you've got these tolerance tubes that are going along all of your edges. And so in Cubit, there's even tools for merging. And we take that same idea and that same idea where as long as these edges are within a certain distance, we can go ahead and merge those together to ensure that we get a conforming mesh across that interface. And so if we start to have geometry, you can imagine I've got a really small edge here. You can see I have a couple really small edges here, that those are maybe completely subsumed by this tolerance circle. And that can lead to then unexpected behavior that can then turn your geometry kind of into a dirty geometry. So I'm going to jump into a few live demos to kind of show these things in practice or in action here. So I've got 4 demos lined up for you today. I'm going to talk about how you can kind of maybe see some spline surfaces, and we'll actually look at the healing operations in Cubit and see that those are where we have issues. Well, then I've got several examples that are primarily focused on electronics and microelectronics that will show where this absolute tolerance comes into play and how you can work around trying to avoid issues with that tolerancing. And then also removing overlaps and cleaning up geometry, especially in kind of native or in orphaned models. And then we're going to just kind of apply a whole bunch of different tools that Cubit has, some that we will have previously shown and some that we'll just show live. So with that, unless there are any questions, I may go ahead and dive right in, Matt.
Yeah, go ahead.
All right. So, oops, I should probably reset this here. So let me get my Cubit session here reset. Okay, so this first model that we're going to show are going to be these clippers. And you bring this model in. Notice one of the things I like to do a lot is I like to see my vertices. This is one kind of good step in trying to help clean up geometry. Is by default the visibility of vertices are off. There's a command that you can run. It's also available in the tools GUIs. I'll show both processes. If we just type vertex viz on or off, we can cycle those. I want you to pay close attention to this curve. How there's actually 2 curves. It's not necessarily easy to see that there are 2 curves there if you don't have the vertex visibility set to on. And so that's one little thing I like to do that kind of helps me easily visually identify where I maybe have some interesting things going on. You can also set that in the tools options. On Mac, I believe it's the Apple icon preferences. And then under, I think it's geometry display, there's a display vertices option here that you can turn on. So there's 2 options to set that. One of the things that you can do, again, we talked about like these spline surfaces. If you had the properties page open, something that's really interesting is that, or I think really cool, is that if you select an entity under the geometry subproperty, it'll tell you what the analytic type of that surface is. And so here it says it's a cone surface. You can do the same thing with curves. And so as we're clicking around, cone surface, plane surface. So those are again like those analytic types we saw previously. But then now one of these surfaces, it now says, hey, it's a spline surface, even though it honestly looks pretty planar. Right? You may not have thought that might have been a spline otherwise. Something that you can also do, if I may have to exit this, where did my little journal files go, is write some Python to actually loop through maybe all the surfaces in your model and identify if that surface type, say, is a spline, we can color it. So this is just a little snippet that I kind of build up just a bunch of little helper Python routines that do a lot of things automatically for me. And so you can find documentation about how to get access to those types. So if we color them, now all of the red surfaces here are a spline surface. So we can see that there's just a few spline surfaces where the majority of these surfaces are actually analytic. But we can kind of see, yeah, that this fillet here is kind of complex, so it makes sense that that's going to have to be a spline. So why does this matter? So probably one of the big tools that you'll use a lot when you have dirty geometry in Cubit is the modify heal command that has also an analyze option. And so I typically, what I'll do is I'll start my kind of CAD workflow by coming in and just evaluating all of the volumes in my model to see where there's maybe some imprecision. So this is kind of telling me that I've got 6 bad vertices, a few bad co-edges, right? And so there's 2 bodies that have these issues. The orange vertices that are highlighted are those bad vertices. And we kind of notice that, right, we're not seeing those bad vertices where I've got analytic geometry. We've got these bad vertices where I've got spline geometry. And that again tends to be where you'll see, if you have spline entities in your model, that's where you'll tend to see issues with dirty CAD. So, I could do some healing operations. I could do an auto heal. Well, this also kind of helps tell me is that I will try to avoid doing web cuts through spline geometry. If it there are ways to turn spline geometry into analytic, but I try to avoid them. So I don't want to I maybe don't want to do a web cut. I do a plane from curve and say for whatever reason I wanted to cut on this curve and do say this web cut or something, right? This is a poor web cut, but this is just an idea of like I wouldn't want to do this kind of a cut, or to say maybe I thought that it would be a good idea to cut through a plane with these 3 vertices to cut that off. I would personally try to avoid doing that style of cut. Instead, I would push my cut off to maybe I can get the same general idea by cutting up here. And now I'm cutting inside of analytic geometry as opposed to inside of spline geometry. And maybe instead of cutting here along, this surface here, maybe I'll cut along or at this vertex out here. And again, try to push it off as much as possible. That's just like one kind of tip to try to avoid exacerbating the dirty geometry that you might have. Because as you do those cuts, you can then more and more damage those spline surfaces. So that's just one little trick I like to do with that. And so we'll make that little Python script that finds these spline surfaces. We'll make that available after this webinar. But that's something I just like to do is find spline surfaces, heal them if I can, but then the ones that you just can't get rid of, try to avoid doing further operations on them. Okay, another model I'd like to show you we're gonna look at a circuit board here. Now, something that is also kind of common in a lot of electronic designs, you can kind of maybe make out just by the rendering here that it kind of looks like I've got overlap of geometry. And that's actually the case. And if you look at this layer here, this layer is just a solid sheet that is automatically generated from a CAD tool. It took a electrical drawing and turned it into a 3D CAD model. And it's just a typical thing that oftentimes happens is that they'll just put these large sheets in the model that then overlap with the actual underlying electrical components. So those are what are called overlaps. So if you were in the command panel underneath the volumes and then this little broom, it's kind of where we have our kind of a lot of our cleanup tools. They're also available in the power tools. Today I'm going to work primarily in the command panel. But in both, there's this ability to manage gaps and overlaps. And so we can detect our gaps and overlaps in our model. And we'll see that here it's found some overlaps here. And so if I look through this, there's really, pair volume 1 to 44, 2 to 44, 3 to 44. There's a bunch of volumes that all overlap with volume 44. And I could come one by one and apply each individual solution that's suggested to me by Cubit to remove those overlaps. What I like to do is I like to do this in Python. So what I might do here is I selected maybe one of these cases that has an overlap. Let's go like 1 and 44. And I say, okay, well, what I want to do is I want to remove the overlap from the larger volume. I'm going to say execute. And that's given me a command. And so what I'm going to do here is, this is how I oftentimes love to work, is I've got my journal editor open on the side. I'm going to switch over to a Python mode. And what I kind of know is I know that I've got a few volumes that, only 2 volumes I really need to subtract things away from. So I'll just start writing Python, where I'm able to call those the large volumes. So there's a list. I've got, say, 44 and 49. For each large ID in those large volumes, I'm going to loop through. I'm going to get a list of all of the entities or all of the volumes that exist in the model at the current time. For each of those volumes, as long as the VID is not in my list of large IDs, I don't want to subtract 44 from itself or 44 from 49. Those will cause some issues. So as long as it's not in large ID, what I can then do is I can then issue this command as a using the Cubit CMD routine, where I can then parse a string. So I will remove overlap. I'm just going to paste in that command that I just ran in the GUI once, and then I'll modify it. And this says modify larger. Okay, well, I do know that I've seen this overlap or remove overlap tool before. It's up here. And I can actually specify the specific volume ID rather than either larger or smaller. So I'm actually going to do that. I'm going to say, okay, well, if it was 1 in 44 and I wanted to remove from 44, what would that command have been? And it's telling me, okay, it's just, instead of modify larger, I just say modify volume 44. So that's easy enough. Again, you're going to use my F strings here. I'm going to remove from the LI the large ID and remove the volume ID from that. So I've spent maybe about a minute or two to build my little Python script here that I can then play. Let's see. Where do I have my little? Probably that knot is probably where it didn't like. Always have it open on the backside. Let's see. That's right. It's not equal to is what it is. Play that. I've now just automated a whole bunch of those commands. I've saved myself a bunch of button clicking and have now removed all that overlap from my model. And so you can see now I've got a very well separated and segmented out layer here. So that's another kind of, it's almost not even dirty CAD as much as it's like lazy CAD. And you see this a lot. I see this a lot with electronic assemblies. And again, if we were to go back to our manage gaps and overlaps tool, we could search through that. And what it's found now is potentially some gaps. And there's this gap distance here, 0.0005. And that's also what the gap distance was used here. So this is where we're going to talk now about, we're going to see this absolute tolerance kind of rear its head. So where do these show up? Well, okay, these are the surface pairs. So I'm going to draw the volumes in surfaces 55 and 457. So what's happening here is that there's actually, you can even draw maybe the neighboring volumes. Maybe it's too much. We'll turn this off. Right, there's this via up here that actually feels like this gap that's between the layer and another, like a bridge here, copper bridge. So the problem is, again, if you imagine we've got these little tubes that are going or covering between these surfaces, that those tubes are essentially kind of inside this gap tolerance that we've set, that we've tried to, that's pushed off from the absolute tolerance. And again, I'll mention what that absolute tolerance actually is in this Cubit. We've set it to 1e-6 for now. But so the possible solutions here that Cubit is thinking is it's thinking, okay, well, I could take this inner surface here and I can merge it, if you extend it out to match with the outer surface here and get rid of like this potential gap. because Cubit doesn't have any other way to know that there's like supposed to be a geometry that's filling, otherwise fillers get to want to imprint and merge with. Or you can go the other way. So if I were to execute this, you can see it's actually like remove that gap suddenly. But again, if we were to draw the neighboring geometries here, right? I've now got that overlap with my purple volume. So the issue that's at the crux here is that now if we turn on our scale, so I've done that by up here on the taskbar here, there's this little, it's got these little axes ticks. If I look at my model, it is being represented right now in units of, looks like these are in inches, I think. Yeah, I believe these are inches. But notice how the thickness here is like 0.06. Now the absolute tolerance in Cubit, you can actually see this if you say set geometry accuracy. That if we don't give it a command, it sets it to the default. And this is 1e minus 6. So anything that's 1e minus 6 or closer, Cubit can't tell the difference between whether or not it's a unique entity. And then you can imagine that then different algorithms in Cubit are going to have their own kind of round off tolerances and issues and errors. And so you want to try to back away as far as possible from that absolute tolerance. 1e minus 6 is kind of industry standard. I don't know of any other CAD kernel or tool out there that provides any accuracy, any absolute accuracy that's smaller than 1e minus 6. It's kind of the tightest you could go. I think many CAD applications, even by default, might be at like 5e minus 4 as their accuracy for performance reasons. What we want to do typically is we want to try to say, okay, well, what's the smallest feature in my model that I care about, that I actually need to be able to resolve and maybe even mesh, a subdivision of. Now, to do that, I could use, again, in this cleanup tool, I could find small features, detect small features. I can see that my smallest curves here are like 0.002, and those are coming in like from where these layers are. So like if I draw this layer, right, like I want to capture this layer, and this layer is eating away maybe a good chunk of my absolute tolerance. So what we tend to, or what our primary suggestion is, to try to avoid various issues that might come. Like if I had to subdivide this, maybe some more web cuts potentially, I could really be in a bad spot. Is to scale your model in Cubit away so that the smallest length you care about is about 1. Now it doesn't have to be exactly 1. What I tend to do is I tend to scale by the nearest power of 10. So say I want to get this from a length of 0.002, I want to get it to 2 as its length. So to do that, I'll be in the volume transform scale. I'll pick all my volumes. I'll scale them uniformly, again, by a factor of 1,000. Don't need this reference point. And we'll redraw everything. So now you can see that my model is now, this height is much thicker. If I were to look at the small, or like one of these edge lengths here, its length is 2. And that's a feature I want to keep. So now if something is actually really small, like say is a size of 0.002 on this scale, it really is just noise that I want Cubit to ignore. This is kind of essentially like a milli-inch unit system now that I've done. So what we need to do is we'll build our mesh here, but I don't want to export my mesh as 67 milli-inches. I want to export it back into an inch unit system. So there is a mesh transform. I can't remember. Should have looked this up. I can't remember where to find it on this board. Maybe someone could drop something in the chat. I typically remember it as just a command line option, which is if we type in transform mesh and hit the question mark, it tells us what our options are here. Then we can transform the mesh on output by a scale factor. So what I'll do is I'll say transform mesh output scale, and using AP Proform, I could do 1 divided by 1,000, or I could just write it out explicitly as 0.001. And so what will happen now is that if I build a mesh here, when I go to File, Export Mesh, it will scale the mesh back down to my original units that I were in. So I'm working in kind of this transformed model to avoid dirty geometry issues and to avoid absolute tolerancing issues. And then I'm recovering it with this transform mesh. And this is why I like to scale by factors of 10 so that these scales are easy. These transform mesh output scales are cumulative. So if I were to do another output scale of 0.1, my total output scaling would now be 0.001. So what you need to do is you need to make sure that you reset. So transform mesh output reset to get yourself back to a scale factor of 1 on output. So what I oftentimes will do is even before I do healing, is when I import my CAD geometry, I'll turn on the scale, I'll verify what units I'm in, I'll kind of peruse my model and kind of try to see if I can tell what the small features are going to be, and then I want to keep, and then I'll immediately do my volume scaling and set my transform mesh on output, and like very first steps, and then I can just kind of work as I normally would. And now we'll see, just to show this, if we look for our gaps and overlaps, because those gaps are now far away, I have that overlap. I created that overlap earlier, which is why that's there. But all of those gaps are now gone because they're far away. Okay, so that was a kind of a deep dive into absolute tolerancing and kind of some of those issues with gaps and overlaps. So let's look at a different model now that maybe shows some other cleanup functionalities on a different, again, still a circuit board kind of application. I'm not going to go through here what it is. I did just scale these by different, again, scale factors so we can look at them. I'm just going to use the millimeter on the space in millimeters here. Actually, no, I want to do the micrometer one. So again, this is something that I maybe have scaled by a factor so that my small length or small edges are far away. This is another model that was auto created by, in this case, Fusion 360. And one of these you can see is that I've got some significant overlaps on these legs on their pads. And again, I want to get rid of those overlaps. And we have that same exact issue with the overlaps of the different traces on our model. So what's nice is because I've written this little Python routine once, I could write this a little bit more, generally in the future. What it is, I looked at this model and I saw that volumes 55 and 56 kind of are those layers. So if I just swap the layers, I'm going to do this remove overlap with. Again, I can just kind of play those through and remove all those overlap, a lot of those overlaps. I'm still going to have to do some manual overlap removal for these legs. So we'll see that here in a little bit once this finishes. Okay, so again, I've got my layers are now sufficiently overlap removed. And again, I could use this manage gaps and overlaps to detect these. And I can come through and manually, I can even say, draw the volume overlaps to see like where this is occurring. So I did that by right clicking on this. Could also fly into it if you wanted to find it. But now what I might do is I might do this as like, I've only got a few of these I have to do this manually with, so I can decide which one I want to remove the overlap from. And so I chose to remove it from the larger volume. You can see that now I've flattened out that pad so it no longer overlaps the geometry. Now there's also something that's, say I wanted to just tep mesh something. You might think, oh, I'm just tep meshing. I don't need to worry about too many things. I don't need it, like, not to the same extent you would with hex meshing. But there's actually some dirty geometry here that would impact even our tep mesh. So if I mesh this volume here with just the standard Hex Mesh settings. Oh, yeah, turn on the mesh visibility. You can kind of see I've got these like little regions where suddenly my Hex Mesh has just like collapsed almost to like a singularity. But why does that happen? Well, if we zoom in far enough, you can see maybe part of the issue here. I've got this really small curve. And even that wasn't really visible out here. And again, we have to remember that this is an example of, this is fine enough for CAD. We just need to know there's an entity that goes here. The CAD tool didn't really care about the fact that there's maybe like this really small little gap. Again, we could find those through our small feature tool to detect all those small entities. If we get in this case, I'd have to change my small curve length because I've scaled this up by a factor of 1,000. So this is actually a really small curve here. So this is an example of, this is where I've taken this curve, when I scaled it by 1,000, its length, you can see, is almost 1. And that's why it kind of avoids some of my detection tools. So again, that's why, what I mentioned earlier, is try to find what the smallest feature you actually care about is, and make sure that that is the entity that's about the size of 1. So in this case, what I have to do is I have to now change my small curve length to maybe like something of size of 2 or something to be able to actually find or have those crop up. If you found those tools, there are various different tools we could use. We could remove anything from remove surfaces, which are actual changes of the geometry, or we could do virtual topology. Let's zoom to this one. Here we go. If we can see what these different techniques would be. So we could say collapse or do some removes of these surfaces. Why is, here we go. Yeah, so we could do some of these different commands to say, maybe we execute one of these. Oh, it's been meshed. That's why it won't do anything. Yep, so we could remove different options here or collapse. So if I do this collapse, so that's just kind of nudge that little vertex over so that we aren't going to force ourselves to fit a tet or triangle there. So those are some options you can do on the virtual topology side, where there's just no other really way about it. Another example is we see like these are essentially facets of like a fillet, and this is going to force me to have to fit a mesh that fits within those. A couple of things you could do is you could do a virtual topology and composite these surfaces together. You may have to try to figure out, in this case, that didn't quite get rid of those bounding vertices. You have to maybe choose like a larger vertex angle for those surfaces to get caught. And there's a volume below it, which is why we're seeing these vertices from the volume below. That's one way to kind of clean up, but that's again happening on virtual topology, which is kind of a step you want to do as a last resort. Maybe like the end, like right before you're about to mesh. But if we want to do CAD operations, one thing we could do is we could turn this into a fillet. How do we do that? Well, we could say remove the surfaces through extending. And I could do this on multiple. I could right click after I've selected these and say select similar surfaces. And actually, let's even first, let's just draw these similar volumes. And actually, I even just want to draw this one volume. Is actually what I want to do. If I just draw this volume, what I like to do is select the surfaces that I want to remove, right click, select similar surfaces. If I zoom out and kind of see what the other surfaces were that got selected, okay, those are all the exact same surfaces on their respective geometries. If I do this remove, it'll make a sharp, it'll extend the neighboring surfaces to a point. And I can now fillet. I forgot to measure what those fillets were, but I think there was like, I think it's 6. Should have measured those first. I'll do that in the next one. Should probably turn my undo to on. That would probably help. And so now I can say select those similar curves, again, making sure that I got those same curves. And I can say that that radius here is going to be 6. Maybe it's 6D. We just do 60 here. There we go. So, there's some like 62.5, but that's just an option where it's now in actual CAD. So just to show how I might have also like measured to get what that entity might have been. If I draw this other surface here, I could actually select, right? This is essentially a circle. If I click 2 vertices, right click and measure, it's going to give me the components of what those distances are. And because these happen to be aligned with X and Y plane, I can see that this is the radius that would want to make that. So 65.125 would be the radius that would turn that blend into. So that's a way that you could then come through. I don't have another better way to turn those into fillets, but in Cubit, I can use these direct editing tools to make those. And I would just go through this entire model and do that. Something else I want to mention too, real quick, if I reload this model, even if I reload, oh yeah, I'll lose this micrometer scale one again. If I do the heel, this looks like there's a lot of complex things going on. If I do that same routine from earlier, if now I just count the number of different types of entities, notice that I don't have any spline surfaces and I don't have any spline curves. Everything is analytic. And so if I go into my healing tool here, so under volume, modify, heal, all of them. Maybe it should be the millimeter one. That's the case. Yep. Because in that micrometer one, I've moved everything so far away from the 0 plane that has issues. So yeah, so on a well-scaled model with all those surfaces being analytics, I actually have no bad geometry in this model yet. And so that's just an example of not having spline surfaces as well as having a good scale in your model versus that, the micrometer one. And if I reload the micrometer scale, I then have quite a few issues in my model. And again, those are kind of happening where we kind of had those issues from before that we'd kind of noticed. So I avoided those by having a good scale in my model. Okay, the last demo I'm going to show today is a spark plug kind of fluid region model that I think you probably saw in the the advertising for this webinar. So first, I'm going to open up the IGES file for it. So this model actually is maybe 20 years old or so. Someone who we've been working with, this is an academic model. It's made available, I think, by University of Michigan, but maybe it's from like the early 2000s, maybe late 90s. And just to show that surface that we saw from previously, that just its representation just wasn't quite able to be captured. And it could be it's an issue in maybe Cubit's ability to render that surface or understand what that surface is, and its translators could, and you'll see that with just whatever tool you use uses certain versions of translation tools that may not be compatible with the version that the original model was built in. What you'll also see is like this IGES file, everything comes in not as a volume, but as sheets. And so it's really a whole bunch of individual surfaces, and it doesn't define any volume. Now, in this model, what the customer cares about is they just want to build kind of a volumetric model of this region, and they actually don't even care about the actual spark plug region here. So using some of our other tools and different versions of the translator, we created a native Asis file for this geometry. Asis being the kernel behind Cubit, so it's native to Cubit. and it actually is able to then have this surface. So what I want to do is I want to get myself down to just kind of like this sub-region. So we're going to kind of walk through steps to do that. And, the first things are, I might look through my model and try to decide, what kinds of length do I want to keep in my model? I know I'm going to get rid of this entity here, but I can see maybe trying to keep something like this. Length of the curve is about 6. That's probably for now about, maybe the smallest feature that I kind of care about. And so, I don't really need to scale this much at all. I mean, I could scale it down by a factor of 10, but I'm going to be pretty well scaled here. So that's kind of check mark number 1. Another thing real quick too, if I just run that this routine to count Asis entities, I just want you to see how in this case we have actually a lot of spline curves and a lot of spline surfaces. If I color them again red, you can just see like almost everything here is a spline. Even though like it looks like this should be like a planar surface and this should be a cylindrical surface. And it doesn't really seem like that should be the case. So if what we do actually is what Cubit can do is if a spline surface effectively is exactly an Asis entity, the auto heal functionality can oftentimes convert those into their spline entities. So here if I color curve all default, color volume all default, and color surface all default, again, to undo all of those settings. If we now were to say count the entities in our model, I've got fewer spline curves, fewer spline surfaces. If we color them, right, it's maybe even hard to see like where they are. They're probably embedded inside somewhere. So anyways, but you can just see that I got rid of a lot of those spline surfaces just with that auto heal tool. That's kind of a really useful thing to be able to do. But what we're going to focus on right now is we're actually going to go ahead and now delete this extraneous CAD that I don't care about. So by control and drag selecting, I can then hit delete on my keyboard and delete those. If I turn on transparency here with the X-ray selection mode, again, I want to get rid of this little spark plug region. So I'm going to select through everything. It's going to, again, get those top and bottom surfaces, which I don't want. So if I control click again to unselect, I can unselect those and then delete. I've now got this hole in my geometry, there's a gap in this top surface, right? So you can see that that's a hole. And yes, this surface has some small entities, but we're going to get rid of this by covering. Again, there is this little small spline curve, but again, we're going to get rid of those by going to surface action modify, create a surface from bounding curves. And then I'm going to make sure to select just these curves. And now I've created a surface that I'm going to then just stitch everything. So I kind of have a few regions here. I've got, notice that I haven't covered these gaps yet. And then I've got these valves on the interior. But if right now, if I just go ahead and stitch these into larger sheets, I should show this in the command too. So volume action modify stitch. If they body all. So now I've got 3 sheet bodies. I've got one just body that got created by accident, just again, kind of like through some dirty stuff that overlaps. So I'm just going to delete this volume through the model tree and compress. So now I've just got essentially 3 regions. Let me color surf all default again. And color curve all default. So let's focus first on the fluid region, this green body. So we draw it by itself. Again, I want to cover these curves with additional bodies. So I've now created a body that's going to cap that. I'll select these two curves. And then also I've got these holes on the tops of these kind of surfaces. Let's color curve all black. We can see that a little bit easier. Now, instead of doing a bounding curve here, because these are, if I look at the actual underlying geometry here, it's a torus. So I can actually just kind of ignore or get rid of those through a tweak. So in my entity curve, modify, tweak, there's a remove option. So I can just remove this curve from that surface. And now it's back to a solid there. And the same on that other curve. And now, if I reset my display, if I do this stitch command between these volumes, I now have, between those sheet bodies, I now actually have an enclosed volume. So I've gone from a sheet body representation of this model to now a volumetric model I can actually build a Hex Mesh on. Now, and what you're seeing here is you're seeing actually the push, or you're looking at these valves on the inside that are bringing their surfaces up. Now I want to get rid of this, right? I got a plane surface on a plane surface. I don't need that anymore. There's also a tool that's really helpful under volume. It's also under surfaces, but volume modify, regularize. Regularize, it's it undoes essentially imprint operations. It removes extraneous entities that aren't required to describe geometry. So if I say choose this volume to regularize, it gets rid of just all those extra curves that I didn't need, that were kind of over defining. Now I've gone away and I have just a single planar surface now. So that fluid region's really good, is looking really good now. Now what I want to do is look at these valves. And if we notice, if I kind of do a cross section through the valve is going to be a plane surface. It doesn't quite fit to the torus. So this is going to cause some issues here. So let's, as a first step, let's just draw volumes 2 and 3. We could cover those curves again. And then we could stitch those bodies. So I'm just going to say stitch body. We have 2 and 7. We have 3 and 8. And so now I've actually got 3 solid volumes. Nothing's a sheet body anymore. But I do want to try to get rid of this little thin sliver here. We do that via a web cut. We typically think of web cutting as a thing for meshing, but it's also kind of a powerful tool here to create our geometry. So if I do sheet extended from surface, what that normally would do is it would take a surface and it would just untrim it and extend it. But instead, I'm going to cut volume 1 with all the surfaces in volume 2, except for this top surface, which is 34. So all in vol 2 except surface 34. And what that's done is it's kept my volume 2, but it's gone ahead and you can see it's done this little extension. It's snapped to the geometry everywhere else, but it just snapped right through and created for me a new volume. So if I draw volumes 1 and 2 here, oops, they're just slightly modified from each other. And so what I want to do is I want to delete now volume 2, which was my tool, leaving just with that modified version of that little valve. And I can do the same with volume 3. Let's draw vol 3. The surface I want to avoid in this extension is 35. We want to cut everything in volume 4. Cut volume 4, everything in volume 3 except surface 35. Again, that little preview that's going to happen with that extend. And then delete vol 3. So after all of that, we now go to our little heal tool just to see, do we have any kind of dirty geometry at all in our model? Because everything is now analytic surfaces as much as possible or everywhere as possible, even just double check how many we have. We only have 4 spline curves and no spline surfaces. And those are just like the limits of those spline curves. So again, I'm gonna have to watch out for these spline curves potentially, these that I've colored white here. We'll have to watch out for them, but now you can see that this model is gonna be very well behaved for us because we got a good scale and a lot of analytic geometries. So there's a whole bunch of more stuff that we could talk about. If I wanted to proceed with web cutting, I would assign blocks before I start web cutting for meshing. We didn't talk about compositing. We have previous webinars where we've talked about compositing and to do the way, but just to maybe as the last thing to end on, and then for questions, I'll just show then the final meshed version of this. I have not spent the time to build a full hex mesh on this, so this is going to be a mixture of tet, pyramid, and hexes. And just to show that I've got this mixture here. Draw ball for 24. Is that gonna? Not sure why our little render has gone bonkers. Here we go. Interesting. Well, anyways, just as a last note that we'll be putting on a demo or a tutorial where we actually build a much more intense hex mesh with boundary layers and everything. But just wanted to show that you can, once you've got that nice geometry, you can go ahead and build your mesh. So I think that's all the things that I have time for. Hopefully that kind of helps give a good overview of the different kinds of tips and tricks to trying to avoid dirty geometry altogether or cleaning it up. If you have any questions or if you want to see those other webinars, you can find them on YouTube, and you can also post in our forum if you have specific questions that you'd like to have us answer. So with that, I'll turn over to questions, Matt.
Greg, thank you so much. This was a packed webinar, and as you know, this will be posted on YouTube, and we'll go through and even segment out the different sections so you can come back and digest this later. I know we're about at the end of the hour. We would be willing to stay on for another minute or two if there's any questions that have come up. So if you have a question, you can go ahead and type that in now.
Yep, and maybe while people are thinking of questions, again, one of the things I'll mention is that we do get a lot of questions again about why Cubit is unitless, right? We don't see like meters or inches and stuff on that. It's something we've thought about, but there is a lot of value in Cubit actually showing you how the data is actually represented in the kernel. And that's what the scale is showing you, is it's showing you that is exactly how it's represented in memory, so that you can actually then interact with that absolute tolerance. So I just want to make that one last emphasis there.
Great.
That I didn't make earlier. So
okay, good. Okay, well, great. We'll let any other questions come up on the form later. But again, thank you so much for the preparation and presentation, and hope everyone has a great day.
Yep. Thank you, everyone.
Bye.